Hello everyone, I'm Thodoris and I'm a PhD student at the Athens University of Economics and Business. I'm going to present our work titled Data-Oriented Differential Testing of Object-Relational Mapping Systems. This joint work with Stefanos Chaliassos, Vangelis Atlidakis, Dimitris Mitropoulos and Diomidis Pinellis. Object-Relational Mapping is an abstraction over relational databases through an object-oriented interface. It boosts developers' productivity and promotes portability. Currently, there is a huge number of ORM implementations used by millions of applications. Here is an example of database interactions using the Django ORM. We have a class, namely model class, that corresponds to a table in the underlying database. We can interact with the database by simply calling methods found in instances of this class. For example, to insert data to the database, we call the method save. To fetch a specific record, we call the method get, while for record deletion, we call the method delete. All these SQL queries are transparent to developers, meaning that developers don't have control over them. Like any software, ORM implementations contain bugs. Let's discuss two indicative bugs. Here we have a code written in Django. We have three queries and we combine these queries through the union operator. When we run the code on top of MySQL, Django produces the following SQL query. However, due to a bug, this SQL query has syntax errors with regards to MySQL. So at runtime we get an exception that says you have an error in your SQL syntax. Interestingly, if we run the same code and the same SQL query on top of a different database engine, the code runs fine. So this means that some ORM bugs are triggered only when the code is run on top of specific database systems. Here is another bug found in the Pigui ORM, a widely used ORM for Python. Here we have a query where we apply two aggregate functions. We apply the function sum on an expression and we also apply the function avg on the square of this expression. That's the query generated by Pigui. Unfortunately, this query is not the expected one because the expression passed as an argument to the function avg is not right because sub-expressions are not evaluated in the correct order. Specifically, that's the expected SQL query, and notice here that the sub-expressions are wrapped by parentheses. Unlike the previous Django bug, this Pigui bug is more subtle because Pigui generates a both syntactically and semantically invalid SQL query. That means that Pigui runs the SQL query without raising any errors, but this query does not produce the expected results. So the question here is, how can we identify such errors? To answer this question, we need to specify a test oracle for ORM-specific bugs. To do so, we employ differential testing, a widely used testing method. The idea behind differential testing is very simple. We have an input, we pass it to multiple equivalent implementation, and then we check the outputs of these implementations. If we identify a mismatch in the outputs, then a potential bug is found in at least one implementation. However, applying differential testing to ORM system is not straightforward. First, ORMs lack a common specification and input language. Each ORM provides its own API exposed in different programming languages. Second, some query results are not deterministic. For example, when we have an unordered query, the underlying database system is free to fetch the corresponding records in any order. As we saw earlier in case of the Django bug, some results are DBMS dependent, and last but not least, beyond ORM inputs, we also need to generate data, because if the underlying database contains no records, every ORM query, and in turn every SQL query, is doomed to produce empty results. So in such a scenario, comparisons between ORM outputs would be meaningless. We propose the first differential testing approach for systematically testing ORMs. Our approach is shown in the diagram and consists of 5 phases. In the first phase, called schema generation, we generate a number of random relational database schemas. We use these schemas in the second phase, called schema setup, where we set up the underlying databases and we automatically derive the corresponding ORM models. Having set up our database and the corresponding ORM models, we are now able to query these models using the APIs of the ORMs at the test. To do so, we proceed to the third phase called abstract query generation, where we generate a number of queries written in an abstract query language used to provide us with a common reference for testing ORMs. In the fourth phase called concretization of abstract queries, we have two things. The first thing is the translation of every abstract query into concrete ORM queries using ORM-specific translators. While the second thing is that we generate targeted data using a solver-based approach. Finally, in the last phase, we have called bug detection. We simply run the generated ORM queries, we compare their outputs, and in case of mismatches, we report a bug. Let's discuss some specific components in a more detail. We designed the abstract query language in order to abstract away differences of ORMs. This language supports a wide range of operations such as filtering, sorting, and many more. Note that this language is closer to ORM APIs rather than SQL. Regarding data generation, we use a solver-based approach. Specifically, given a query written in SQL, we encode it as an SMT formula. The encoding process is described in detail in the paper. So, having obtained our SMT formula, we pass it to a theorem prover, and this theorem prover checks if the formula is unsatisfiable. If not, the theorem prover provides us with a counterexample. This counterexample stands for the data inserted into the database. In practice, we actually derive insert statement from this counterexample used to populate the underlying databases. So if an SQL query is satisfiable, we guarantee that there is at least one record in the database that satisfies the constraints of this query. So ORMs always produce non-empty results. We have implemented our approach as a tool called CYNTHIA, written in Scala. CYNTHIA uses the Z3 theorem prover and currently provides support for 5 popular ORMs, namely Django, SQL Alchemy, Peewee, SQLize, and Active Record. CYNTHIA runs the generated ORM queries on top of 4 popular database engines, namely SQLite, MySQL, PostgreSQL, and Microsoft SQL Server. Within 4 months of testing, CYNTHIA has found 28 bugs, most of which have been fixed by developers. Note that there is a significant number of DBMS dependent bugs, so this validates our intuition to test ORM implementations across different database engines. We also measure the effectiveness of our solver-based data generation, so we compared it with a naive approach where we generate random records without considering the constraints of the generated queries. To do so, we spawned 20 testing sessions consisting of 100 SQL queries and measuring how many queries the ORMs returned empty results. As you see in the diagram, when we use our solver-based approach, around 8% of the generated queries are unsatisfied. This is because either the generated queries were unsatisfiable or the solver timed out. On the other hand, when we use a naive approach, around 38% of the generated queries are unsatisfied. Notice that even if we increase the number of records, we get no improvement. So generating 50 random records is almost the same with generating 1,000 records. To conclude, we have introduced the first differential testing approach for systematically testing ORM implementations, and we showed that differential testing can be also applicable to seemingly dissimilar interfaces such as ORMs. We also showed that compared with other simplistic approaches, our solver-based approach for generating data is suitable for differential testing. Our implementation, CYNTHIA, discovered 28 bugs, most of which have been fixed by developers. As future work, the effectiveness of CYNTHIA can be further improved by considering other forms of queries or the transaction management implemented by ORM systems. Thank you for listening.
Hello, everyone. Welcome to this Q&A session. I hope you enjoyed the second paper presentation. I'm here with three of the authors of the paper, Stefanos, Todoris, and Diomidis, and we are happy to take your questions. So please use the chat to ask questions, and don't forget that at the end of this Q&A session, you will have the opportunity to join the authors in their breakout room for direct interaction with the author. So far I don't see questions in the chat, so I will take the opportunity to ask the first question. So based on the examples in the presentation, it looks like that bugs are often related to tricky combination of operators in usage of the operators in the query. I wonder how often applications that use ORM, the ORM technology, have the kind of faults that you discover with the testing, the test case generation approach that you present. So how common they are in the application that you use ORM application? I don't know if you have any insight about this.
Thank you for the question. Actually, operators such as aggregate functions are often used. I think that are often used in applications because typically you may want to aggregate data, you may want to perform, for example, the sum of something, things like that, or you may want to create more complex computations. So you have sub-expressions, and these computations, you want these computations to be performed correctly.
Okay, I see. But you don't have any. You have not studied this aspect empirically, let's say.
Yes.
Okay. And maybe another question while we wait for the audience to ask questions. Is the schema generation capability able to cover every possible situation or the full power of the ORM mapping? I'm thinking to cases like, for instance, inheritance that requires a specific schema in order to be covered. And I wonder if this is in the scope of the test case generation technique.
For schema generations, the things are quite simple. Actually, initially we generate database schemas. We generate tables and columns for these tables, and then we may have relationships between these tables. And then from this schema generation, we use existing tools to automatically derive the ORM models. One possible situation that we don't cover is that we don't cover many-to-many relationships, and we don't cover, for example, the constraints on columns, for example, unique constraints, because we thought that these constraints do not actually affect the translation mechanism implemented by ORMs. So having a constraint does not affect the translation of ORM query or specific ORM query. But I think that it would be an interesting possible situation, for example, to test not the translation of ORM queries, but to test the schema translation, the database translation, how these things are handled by ORMs.
Or have you, for instance, talked to testing the entity manager? In this case, all these constraints may play a role, because in this case, you will be testing the service that is used by the application to manage the mapping. And then, like these unique constraints may have an impact if they are not well handled by the entity manager.
Please repeat your question.
I wonder if you talk to testing the entity manager. The entity manager is the service that can be used inside like the application that exploit the ORM mapping. And in this case, when the application uses the entity manager, I'm referring to the case default might be in the entity manager in the service, not in the translation. And in this case, like the unique constraints, the cascading effects, all those elements may play a role in a bug. So you might need to cover some specific situations to discover a bug. So just wonder if you talked how and if the approach can be extended not only to cover the mapping, but to cover all these other elements that are part of the ORM mapping.
Yes, actually, yes, as I said before, this possible future direction to test the entity manager, because as you said, indeed, these constraints and how the database schema is used affects this entity management entity service. As another example, you may consider the transaction management implemented by ORMs. This is another possible future direction to test. Or another possible direction is write queries. So far, we test read queries. We chose these queries with this type of queries because we thought that they are more promising to find bugs. But all these are promising extensions of this work.
Yeah, I see. I don't see any question in the chat. Maybe just one point, since you mentioned the read queries. I think the test case generation process exploits the fact that the query returns actually a result, so that it is a read query. So how the technique will change in order to cover like the insert or update queries?
I think that to test write queries is that, okay, I have a record, I test this, I insert this record, and then you can perform a read query to see that this record is indeed stored in the database. So if you don't want to perform this read query by using the ORM, you can simply perform an SQL read query. Okay, so you may assume that the database engine is right, is correct, and yeah.
I see. You can run a follow-up query.
If you allow me to add there, in
Sure.
an update query, you can have specifications. So where, in the same form as we have in selection queries, so this can be reused. The fields can be reused, and in addition, we need to generate the values that will be inserted. And for this, some selection of values, extremes, nulls, and so on will be needed.
I see. Correct. Okay, so I think we are running out of time. We have 1 minute left, so I exploit this minute to thank the authors for attending the session and also the audience. And again, let me remind you that there will be this opportunity to meet and interact with the authors joining the breakout room just at the end of this Q&A session in 40 seconds from now. And thanks again for attending.
Thank you for sharing and the interesting questions.
Thank you. Thank you.
Ωραία, ερωτήσεις δεν είχαμε δυστυχώς, αλλά καλά πήγε. And we are live,
Hello, I'm